Hey guys, welcome to the last section, or what I believe the last part will be of chapter number 7. We've so far talked about energy. We've talked a little bit about heat and work and how we can use those to calculate energy. And now what we're going to do is we're going to talk about enthalpy, right? So enthalpy and energy are very similar, but not quite the same. And enthalpy is the sum of the internal energy and the product of its pressure and volume. We'll go to the board in a minute and look to see what that is. So it's slightly different, right? It's not exactly the same enthalpy and energy, internal energy, but it's very similar. And what we can use enthalpy for, and what's going to be very important is the sign. Again, it comes back to the sign. If delta H is positive, it is known as an endothermic reaction. Again, what about the system? If the sign is positive, where is the energy, where is the heat going? It is going into the system, right? And so the heat is absorbed, or the system is absorbing the heat from its surroundings. And so you have a picture there of one of those instant cold ice packs where you break it up, you shake it. It's a chemical, it's an endothermic chemical reaction. And so all of the heat is rushing into the system, to the reaction. And so it feels cold. Whereas if delta H is negative, then it's known as an exothermic reaction, like this flame here, right? The heat is then going out from the system into the surroundings. And so let's go ahead and look at this delta H. And let's go ahead and we'll look at a couple things real quick. And while we do that, we'll be able to notice a few things here on the board. And so again, I apologize for the glare, but that top line is the equation for enthalpy, right? Enthalpy is H is equal to the total energy of the system plus, right? It's the sum of the total energy of a system plus the product of the pressure volume, right? So work. Well, enthalpy can be denoted as a state function, right? Which is the next line. So we have delta H equals delta E plus P delta V. So we've seen some of these things before. And again, we're just going to maybe quietly change a couple things. One of the things is, the internal energy we saw before is Q plus W, right? The total internal energy of a system is the total amount of heat plus the work that that the system can do, right? And now notice I put a little subscript P next to the Q. This will be important because we're going to be talking about doing things at constant pressure, right? So at constant pressure. And then P delta V is equal to negative work, right? Because remember, it's the work done to the surroundings. And so that would be negative work. And so what we can do is just plug in for delta E QP plus W and for P delta V minus W. And the works will cancel. And what we get is delta E H is equal to Q at a constant pressure. Now, what we can do, right, and this is very important. This is, we'll look at 4 different ways that we can calculate enthalpy, right? There's 4 different ways we can calculate enthalpy. One of the ways we'll see is through a chemical reaction itself and us measuring some things. And so what we can assume then is that the Q at a constant pressure is equal to the Q of the reaction that we're going to look at. And obviously we said QP is equal to delta H. So then Q of the reaction is equal to delta H. And so we'd be able to find enthalpy through a reaction that we do in the lab. And so let's go ahead and come back to the PowerPoint. And we're going to talk a little bit about enthalpy a little bit more. And so enthalpy, right, is dependent on how much you have, right? So the enthalpy of the reaction is known as the heat of the reaction, delta H of the reaction. Again, these little subscripts are very, very important when we talk about delta H. So delta H of the reaction is the amount of heat generated or absorbed when the chemical reaction occurs, depending on the reactants. And so we have propane, which is C3H8. In 1 mole of propane, right, we burn it, we combust it, we can get negative 2,044 kilojoules of energy. Now, I want you to think about things. So for 1 mole of propane, we combust it. We get negative 2,044 kilojoules. Is that an exothermic or an endothermic reaction? That's right. It's an exothermic reaction because there's a negative delta H. Now, let's say that's for 1 mole of propane. Let's say we had 5 moles of propane. What do you think we could do to delta H of the reaction? That's exactly right. We would multiply it by 5 because we'd have 5 times the amount. And what you would end up getting is about 10,000. Now, propane is the stuff we use to heat our grills. Usually, some people use propane to heat their grills, right? And now you see why, because there's so much energy, potential energy, that we can then release, right? Negative 2,044 kilojoules every time we burn 1 mole of propane, and we're using a lot more than 1 mole when we grill. And so, right, this is what enthalpy can tell us. So then how can we measure enthalpy? I told you guys there's a couple different ways that we can measure it. Here's the first way that we can measure it. We can go into the lab and use what's known as a coffee cup calorimeter. We will be doing this in a lab later in the in a couple days. Coffee cup calorimeter measures at a constant pressure, right? We talked about delta H of the reaction is equal to QP, which is equal to then the Q of the reaction. Now, when we talk about the reaction, right, we need to think about a few different things, okay? Let's go back to the board and let's look at this real quick. So we're gonna look at the coffee cup calorimeter. This is different than the bomb calorimeter. We're actually not going to be calculating anything with a bomb calorimeter, but we will with the coffee cup calorimeter. So we are looking at delta H of the reaction. And we already said that it equals to QP, and so then we can assume that then it's going to equal Q of the reaction. Now, this is Q of the reaction. In a coffee cup calorimeter, let's go and set this up. In a coffee cup calorimeter, we actually don't measure the exact chemical reaction because we can't, right? It's impossible to measure the atoms and what happens. But what we can measure is what's known as the Q of the solution. Now, let's think about this. We have Q of the reaction, and that's going to be, right, that's going to be the system. This is going to be the surrounding is the solution. So what sign has to be on the Q of the solution? Exactly, is a negative sign. Now, let's think about this for a second. Does this make sense? Does this make sense? So let's say we are to look at an exothermic. Right? Remember the sign of delta H for an exothermic reaction. It's going to be negative. Right? So let's think about what's going to happen to the solution. The solution, the temperature is going to increase. So the final, T final minus T initial is going to be positive. But wait, Dr. Bishop, you said that exothermic is negative. That's right. This is why this sign is very, very important in this type of equation. This is why the signs are so important, right? And this is why, we kind of have to get our mind wrapped around some of these different things. Now, Q, we're going to solve it the same way we solved it before, right? Where it's equal to the mass of the solution times the specific heat of the solution times the change in temperature in Celsius. And so we'll be able to tell a variety of different things when we do a coffee cup calorimeter. What's another way we can calculate delta H? We need to learn about a few relationships we can do with delta H for this way, and this is known as Hess's law. So we might not be able to directly measure the delta H of a reaction, but we know the delta H's of some smaller reactions, and what we can do is we can then add those together, and we can come up with an answer. And so If a chemical equation is multiplied by some factor, and we'll walk through a problem like this because I really like these problems. I really, really do. If a chemical equation is multiplied by some factor, then delta H of the reaction is also multiplied by the same factor. If a chemical equation is reversed, then delta H of the reaction changes sign. And if a chemical equation can be expressed as the sum of a series of steps, then delta H for the overall equation is the sum of the heats of the reaction of the steps, right? And so what happens is, like I said, if you have a bunch of different little equations that equal the equation you're looking for, you can add all those up after you manipulate them if you need to. And then what you can do is you can then calculate them just by adding. And so what I'm trying, here we go. And so let's go ahead and quickly do a question on the board here. So I will show you one, and then there will be one that is probably given to you on your homework, or at least on another practice. So we want to know, making carbon monoxide. Carbon solid plus O2 gas, H2O gas. States of matter, again, are very important. And I want to know what the delta H of the reaction is of this. Well, we don't know exactly. We can't measure it. It's really hard to measure. And so let's go ahead, and I'm going to tell you that we know this equation. Gives us a delta H of 393.5 kilojoules. And so what I'm going to do is I'm just going to go ahead and pause the recording. All right, we're back. I just went ahead and wrote down the other equations that we would need. So we were, again, remember, we're looking for this reaction up here. We're looking for the delta H. What we have is, we know that solid carbon plus oxygen gas gives us CO2, and there's the delta H, negative 393.5 kilojoules. We know that 2 carbon monoxide plus oxygen gives us 2 CO2. The delta H is negative 566 kilojoules. And then we know we have 2 H2 plus O2 gives us 2 water vapors. The delta H of the reaction on that one is 483.6 kilojoules. And so what we want to do is we want to look at these equations up here, and we want to make sure everything is lined up exactly the same, right? So let's look at this first one. This first one, we have carbon solid as a reactant. We have CO2 gas as the product, but really there's only one thing we can use in this equation that matches our problem equation, and that's this carbon solid, but it's on the right side. So if it's on the right side, which means reactant side, you just kind of put a check mark. Nothing can we don't need to do anything with it. Now let's look at this one. Ooh, carbon monoxide, we need that one. Oh, but on this one, it's on the reactant side, and ours, it's on the product side. Okay, well, what can we do? Well, what we can do is we can reverse the equation. So what we can do is just take this equation and flip it. Well, let's just think about that real quick before we do that. Here we have how many moles of carbon monoxide? We have 2 moles of carbon monoxide. How many moles of carbon monoxide do we have here? Oh, we only have 1. How do we go from 2 to 1? Oh, that's right. We can multiply it by, so I would say multiply it by 1/2. You can divide it by 2, multiply it by 1/2. It's the same thing. So what we're going to do is we're going to flip this equation. When we flip it, remember our rules that we talked about in the PowerPoint. If we flip it, so right now we have CO plus O2. CO2 goes to CO plus O2, right? So we flipped it. So our delta H has to now be positive. That's right. But we didn't only flip it. So let me just go ahead and do this. So we flip. but we also multiplied it by 1/2. And so if we multiply the equation by 1/2 to get CO2 goes to carbon monoxide plus 1/2 O2, we also have to multiply the delta H by 1/2. And when we do 566 times 1/2, we get a 283 kilojoules. And remember, it's positive, so 283 kilojoules, and it's positive because we flipped the equation. Let's go and move this up. There we go. Maybe we can see it better. Now, let's look at this equation. Oh, H2, I need that one on the other side. Ooh, H2O gas, oh, but on the other side. And oh, look, we have 1 mole here and we have 2 moles here. So we're going to do the exact same thing that we did to this equation. We're going to flip it, and then we're going to multiply it all by 1/2. Again, we're going to go through, this is a pretty quick, not pretty, it is a quick run through of these. If you feel like, Dr. Bishop, I just had no idea what you just did here or what you just said, please let me know. And we can schedule a meeting, or we can do something where it's a little bit slower, take lap time to actually walk through this a little bit slower. And so it's 241.8 kilojoules, but again, it's positive because we had to flip around the equation. So now why do we do this? Right? Why do we do this? So that we can have fun now. So remember, these are done. We're not looking at those anymore. We're just looking at these two. So if you find something that's on the reactant side and the product side that is the same, you can cross it off. This CO2, it's gone because it's there and there. This O2, so we have 1 mole of oxygen here. We have 1/2 mole plus 1/2 mole. That's going to be 1 mole. And so what are we left with? We are left with carbon solid plus H2O gas gives us carbon monoxide gas plus hydrogen gas. All those look very familiar and are on the same side as what we're looking up here. And according to Hess's law, to calculate, so we don't need these, to calculate the delta H of the reaction, what we need to do is we just need to add minus 393.5 plus 283 plus 241.8. And when we do that, we get a plus 131.3 kilojoules. So then I ask you, is this an endothermic or exothermic reaction? That's exactly right. It is an endothermic reaction. It requires an input of energy for it to occur. And that is a lot of stuff right there. This is my favorite one, if you will, my favorite way to calculate delta H of the reaction, because it's like a big puzzle. So there are even more convenient ways to determine delta H of the reaction, usually performed when you're looking at a large number of chemical reactions. We want to know delta H. You know, a lot of times we would just want to know what delta H is, not the absolute value of H. And so what we can do is we can start defining a standard state of enthalpy. And that's where those little knots, you can see standard state, you can see standard enthalpy change, and you can see standard enthalpy change of formation. And all of these have an independent equation. And so how can we define these? And so, but first, I just want you guys to look here. Here's a problem that you guys can do, like what we just talked about with Hess's law, where we're trying to make propane. And I would like you guys to figure out what the delta H of the reaction is for the formation of propane. All right, the last thing we'll talk about is how do we define the different states? Standard state for a gas, it's at 1 atmosphere. For a liquid, it's usually at 25 degrees Celsius at a pressure of 1 atmosphere. For a substance, it's at 1 molar. The standard enthalpy change, right? So we're talking about standard states. We can then calculate standard enthalpy change, which is the change in enthalpy for a process when all the reactants and products are at a standard state. And because of that, we can then calculate how much energy it takes to make something. And so for its pure compound, right, the change in enthalpy when 1 mole of the compound forms from its constituent elements, if there's a pure element in your reaction. So we looked at carbon solid. The delta H naught of F, if we're going to use this way to solve it, is 0. So how do we then calculate it? I am glad you guys asked. First things first, we need to have this table to calculate it. If I ask you on an exam to calculate delta H naught of F or delta H naughts, then I would need you to give you this. Notice a few things. Again, elements are 0. Notice the signs of a lot of these things. A lot of the signs are negative. There are some positive, but some of them are negative. It just goes to show you the energy that it takes to make them. This can be found in your book, just a smaller one. A larger one can be found in the indexes in the bottom. So then how do we calculate this? We calculate it by this equation. The number of moles times whatever the formation is of that molecule for each of the products. We're going to add them all together, the products, and then we're going to subtract all of the reactants. So now let me just walk you through with words how to do this. And then I'm going to show up a problem for you guys to then do. And then I would like it if you guys could send me the answer. If you could send me the answer just to make sure that you guys are on the right track. And so here we have ammonia plus oxygen gives us nitric gas, and then or NO gas and water vapor. Now, products minus reactants. And remember, we need to know the number of moles. So what we would do is do like 4 times whatever the delta H naught of F of NO is, plus 6 times whatever the delta H naught of F of H2O is. We'll add those two together and we'll subtract it from, and do the same thing for the other side. We'll subtract those two, get an answer, and that's the delta H naught of F, or the delta H naught of this reaction. Hopefully we went through this pretty quickly. I understand. Hopefully if you have any questions, please let me know. This ends chapter number